Hi everyone, here we are in Module 4, and I realize that this module has quite a bit of complex information that's been presented to you, and so my hope is that in continuing to provide these uh, brief presentations for most of the modules, that it will help you to clarify the information in your own mind, pull out the really critical details that must be understood in moving forward, and so on and so forth. I've received some feedback from some of you saying that these presentations are helpful, and that is indeed an encouragement, and so I will continue to make them. For this module, what we're looking at is the statistical analysis of simulation model output, and perhaps even more broadly than this, how should you run a simulation so that you can get data to analyze? And so this module presentation will take a look at that. So in my mind, there are three things that need to be considered. The first is understanding and identifying the type of simulation model that is being studied. And I think that the literature this week was pretty clear about that. Secondly, how many replications of the simulation, sometimes these are called simulation runs, how many of these are necessary in order to generate enough data to analyze it? And then finally, how should the data produced be analyzed once the runs have been produced? So once we've run a significant number of replications, what do we do with the data that the model has produced? So looking at our first topic, what kind of simulation are we looking at? There are really two types of simulation processes. There are terminating and non-terminating simulations. The term terminating refers to stopping, and so a terminating simulation is one that has a defined starting and stopping point. The system is cleaned out at the end of the process, and we're familiar with these. A terminating simulation would be one where the system starts empty and it ends in an empty state. So an emergency room, I guess if it closed, that might not be the best example, but a doctor's office. So a doctor's office opens in the morning. At the beginning of the day, there are no patients in that office. And at the end of the day, when the personnel leave, there are no patients. A store that has defined hours, this would be a terminating process. On the other hand, non-terminating processes, these are continuous processes that don't have a defined starting and stopping point. So for example, if you have an assembly line manufacturing process where there are multiple shifts running each day and the system is never emptied or cleaned out, this would be an example of a non-terminating process. A non-terminating process is going to reach a steady state. In other words, when it first starts up, obviously it's not going to run in a normal way as things get online. But once the system has stabilized, it's going to have stability. And at that point, we would start generating data from our simulation. And so these two types of systems are different, and data that is produced by these kinds of simulations needs to be treated differently. And that's primarily due to the warm-up period that's necessary in a non-terminating process. You probably read about this. I think all of the articles that you looked at this week talked about that, and I think it's pretty clear that these types of systems are not the same. We have to keep in mind that if the inputs going into a system are stochastic or random, the outputs are also going to be random. And this was discussed a couple of weeks ago. Some of the random inputs that we've discussed already are things like service times, mean time between failures, and that kind of thing. So recall that model runs must be replicated multiple times. You wouldn't just run a simulation model once and say, okay, I've run my model. Now I'm going to collect the data from that single run and make some inferences from that data or make decisions from that data. We would rather run a simulation multiple times. We call these replications, and then make conclusions about the output data after running multiple replications of a simulation. And so the question is, how many replications must be run in order to get data that one can be sure is sufficient? So here we are back looking at some common statistical discussions, because you have essentially a population of data. If you just ran that simulation constantly, you would have lots and lots of data, just like you would have coming from your actual physical system. And you could sit there and measure it for years, and you'd probably be able to make some pretty accurate conclusions, but that just isn't realistic. And so you need to create a sample of data from which you are going to make decisions. It's impossible to gather the entire population of data, and so one must obtain a reasonably large sample in order to make statistical inferences from the data. So in a terminating simulation, this is one that is going to start and stop. The focus is going to be on performance during a particular time period. So you're not going to reach a steady state with a terminating simulation, but you are going to have a defined starting and stopping point. And you can have a certain shift. You can have a week of work, you can have a day of work, but the focus is going to be how well does the system perform within a certain time period. And performance can be measured according to what the interest of the simulation practitioner happens to be, or of the whoever's in charge of the simulation. But you may be asking questions. A lot of questions are about throughput, so that can be a performance parameter that is examined. Another could be defects. Another could be machine uptime or machine downtime. So there are a number of different parameters that can be measured and quantified during both a terminating and a non-terminating simulation. So as I said before, the system is clear at the beginning and empty or idle at the end. And the literature seems to indicate that if you have a large sample size or more than 50 replicates of your simulation run, you're going to have substantial data for analysis. Now you think, well, that's a lot of time to run my simulation. Let's say that we're running an 8-hour shift and we're going to run that 50 times. That's a lot of time to run a simulation. But keep in mind that using a simulation software package, you can accelerate the time for the simulation. So for example, in FlexSim, which is the software package that I've been trained to use and that I'm most familiar with, I can run a simulation for quote unquote 8 hours on the computer, but it may only take a matter of minutes to run that simulation using the PC. And so when I say that we're running 50 replicates of an 8-hour shift, that is not going to take whatever 8-hour shift times 50, so that's not going to take 400 hours to actually run that. It's going to be just a fraction of that amount of time. So In a terminating simulation, you're going to examine a random output variable from the simulation over multiple replications, and I've just mentioned what some of those could be. So you could look at throughput, machine uptime, machine downtime, worker utilization, quality issues, and things like that. So you're going to take a look at a variable, and you're going to take that variable for each of your replications and get a mean. And then, of course, the number of replicates, the larger that it is, the more accurate your mean is, just as you've learned in basic statistics. So the sample mean should be comparable to the true mean for the variable. And the central limit theorem is going to indicate how close that sample mean is to the true mean. And if you want more clarification about the central limit theorem, I'm posting a resource in the notes underneath this video that is a good explanation of the central limit theorem, and that may be helpful to you. So now what about a non-terminating simulation? Well, it's very similar in the analyzing with statistics as a terminating simulation would be. But the difference here is that you've got a warm-up period that is necessary in a non-terminating simulation. So let's say that you're getting you're simulating an assembly line in your simulation software. And when you start your simulation, that assembly line is going to be empty. There will be no parts on the line. There will be no breakdowns on the line, hopefully, and it just won't be operating as normal because it's not full. It hasn't been populated yet. And so a warm-up period is necessary to get the assembly line into reaching a steady state. And hopefully that will help you to understand how really a non-terminating simulation differs from a terminating simulation. The terminating simulation, remember, never reaches a steady state. It's empty, it's full, and it's empty. And it isn't online long enough to reach a steady state. On the other hand, your non-terminating simulations, your continuous processes, will reach a steady state, and so we have to account for that. So very simply, I think the simplest method for looking at data from a non-terminating simulation is to use a method called Welch's method. And this involves graphing one of the parameters in your system until it stabilizes. And then you delete the portion of the replication prior to that point. So you would basically, in layman's terms, you're going to not use the data from the warm-up period. You're only going to use the data from the steady state. And I think the law paper, the first paper that's listed in your readings, does a good job of describing this. So how does this apply to you? Well, if you were overseeing or conducting a simulation, you would want to be really sure that if it was a non-terminating simulation, you were not using data from the warm-up period. You would want to run that simulation for several hours or days in the simulation terms in order to get it to reach steady state, and then use only steady state data in your data analysis. So let's just get up to the 30,000 foot level here for a minute and look at our confidence intervals. Just seeing the big picture. Remember that when you run your simulation, you are just creating a sample that you're going to evaluate, and that sample is just a snapshot of the population that's being studied. The greater your sample size, the more accurate your snapshot. Now, obviously, if you made your sample size infinitely large, it would be a mirror image of your population. And that is just not feasible to have such a huge sample size. So you need to have an appropriate sample size in order to get an accurate depiction of what's really happening in the population. Remember the purpose of your simulation. What is it that you're trying to study here? And is it going to mirror the real system that is being evaluated or not? And hopefully, as you back up and think about this in evaluating your simulation, you're going to realize whether you are having too many simulation runs or whether you're looking at an appropriate number. Now, in the literature, and especially I thought that the law article had some really good examples. Probably the best example for a non-terminating simulation was on page 69 and page 70, and then a terminating simulation was on page 71, where they talk about the manufacturing system there at the bottom of the page. So I hope that that's helpful to you. And I just want to end this presentation with the reminder. I love Zig Ziglar. I'm not sure if you're familiar with him. Anything that he wrote or any talks that he gave were just so helpful for anyone, whether they were in sales or not. That's what he was in, was sales and motivating people who are in sales. But what he said is, what you get by achieving your goals is not as important as what you become by achieving your goals. I just want to challenge you during this module, as you kind of dig through the information that has been provided and look at these concepts, that you realize that working towards having a fundamental understanding of simulation processes is going to help build your confidence in technical terms, in terms of being able to help manage a simulation project, which we'll be looking at in the next module, overseeing one, and having a really solid foundation in understanding when simulation is appropriate and how it can be helpful and beneficial to any organization. And so remember that the goal here, and the goal that you should be achieving, is to obtain that good solid knowledge of simulation fundamentals, so that then you can go ahead and deepen that knowledge if you wish to learn more about being a simulation practitioner. But more likely, if past students are any indication, you have a good working knowledge of what simulation is, how you would manage a project, and how you may work with a simulation practitioner in order to help your own organization to be more competitive. So please remember to focus on that. And I'm just really proud of each of you for continuing on, and I'm looking forward to the rest of the semester with you. So we will see you during Module 5.